Also, one should say, you've probably seen the black hole image of M87,
Yes.
this famous orange ring picture which was there. I think we really can expect at some point a similarly good or even better image of such a star. I do know that data have been taken, excellent data, and the Event Horizon Telescope team is working to get such an image.
What's up, you scholars of enlightenment? We have a very special Nobel Prize centric Bad Boy Meets today. So many of you probably know that the Physics Nobel Prize for 2020 was shared between 3 physicists for the work on the phenomenon of black holes. So Professor Roger Penrose for his theoretical work showing that a black hole could form in reality, and then Professors Andrea Ghez and Reinhard Genzel and their teams for their painstaking experimental work to show that there might be a black hole at the centre of our very own galaxy. So to help us understand, discuss and unravel that painstaking experimental work, we welcome to the channel Dr. Stefan Gillessen of the Max Planck Institute. He's a member of Professor Genzel's team and an astronomer who's been looking at the galactic centre for over 20 years. So Dr. Gillessen, welcome to the show.
Hello, I'm very happy to be here, and I'm very excited to do this modern format of introducing myself. So.
Exactly. Thank you very much for taking the time. And you have said I can call you Stefan, so anyone who's watching this is fine from now on. So first of all, congratulations on your work. And how does it feel to be part of a team that won the Nobel Prize?
It's really just a very, very happy feeling, which you have. It's actually something, I mean, I'm only a small little wheel in a bigger team. I mean, Reinhard Genzel got the prize, and I think I was among the first to see him after that famous call. I mean, he said it was really like he was in a Zoom meeting, what people nowadays do all the time. Comes this
as we're doing right now. So
and there comes this strange number on his phone. What is that? And the first thing they say is, "This is Stockholm." It's really like that. And they actually call at 11:25 when the announcement is at 11:45. So there's a 20 minutes before the public knows, so he knew before. And I then actually saw him stumbling out of his office. He was literally, he almost crashed into a door or a wall. And the first sentence he made was actually just the word Nobel Prize. Then he moved on and then came back. And on the second attempt, then was able to form a proper sentence, but only saying that you need to watch this announcement. And in the third sentence, he was then able to explain that the announcement will be about him. And and that I mean was unbelievable.
I remember working on the LHC in 2012 when the Higgs Prize was announced, and having a similar feeling of, wow, this is amazing. Being close to this is it makes you feel like the work was worthwhile, even though you're a tiny part of the whole thing.
Yeah, and I think it's true for many Nobel Prizes which went to big experimental teams, simply because experimental work nowadays requires so many people to be involved, and it's not that you can have a professor, 2 students, and maybe 3 people from a workshop who can set up a machine which does Nobel Prize worthy work. You need bigger machines than that, and that's true in astronomy as it is for particle physics, of course.
Yeah, that's very true. So there've been many Nobel Prizes recently that have gone to astronomy. 3 out of the last 4. Are we in a golden age of astronomy? Why is this happening? What are the most current exciting things going on in the field?
Absolutely. I mean, astronomy really is extremely exciting, and I can only say that I was excited about astronomy when I was a small boy, at the age of 12. I probably started it. And I think that excitement has come to full fruition in a golden age now, because astronomy discoveries are everywhere. And maybe the point is a bit that in astronomy you can, by properly observing, you can get to very extreme laboratories. You can get into things which you usually cannot cannot reach on Earth,
Yeah.
if you think of black holes or Big Bang. On the other hand, it immediately always touches everybody who is listening to some astronomy news, because it immediately asks the question, what is our place in the universe?
Yeah.
It makes you feel small as a little person just sitting here on this little dust grain revolving around a very ordinary star in this big Milky Way. So it's indeed a very exciting field to the public. And scientifically, I think it has come simply to a certain maturity in terms of instrumentation and telescopes. We have routine operations nowadays with very large telescopes of the 8 to 10 meter class. We have reached levels of accuracies in many respects, which are simply factors hundreds of thousands better than what was possible before. And that opens up so many things. And I think this opening up, this is the big difference to many other fields of physics. In astronomy, we are still opening up completely new regimes, whereas other physics fields are probably pushing for factors 2. In astronomy, it's sometimes a factor 100 happens.
It's very interesting what you say, actually, because we see a similar problem in particle physics. Obviously, we have a 27-kilometer long ring at the LHC, and people are saying, should we bother building another one for another factor of energy? And a lot of experiments like the Pierre Roget experiment down in South America are looking to the cosmos for these extremely high energy particles. Obviously, the flux is more difficult. The probability of getting these to hit your experiment is more difficult. You need these huge experiments. But as you say, you can get to these new regimes. So even in particle physics, we're looking to space as well. So it is very interesting, new regimes. And it's nice. I think it's nice in the last couple of Nobel Prizes that we've seen that mix of theory and experimentation as well, which shows the whole scientific method being honoured, that coming up with a hypothesis, testing it, and then bringing the two together. It's nice to see.
I mean, that's true for the Higgs as well as for the gravitational waves. Maybe a bit less for the exoplanets, which was last year's Nobel Prize.
Yeah.
But of course, the exoplanets is really a field which has so much added to astronomy. It's a very rich field. It's moving a lot. A lot of young professors are hired in this area. Yeah. It's not my expertise. I'm working on this black hole in the galactic center, but I can see that this is it's a blooming field, and in particular, also the instrument which we have built to observe the galactic center is actually also an excellent machine for exoplanets, in the sense that it might be a very good way towards measuring the atmospheres of exoplanets. And that is, of course, something which tells you about composition and so forth. So
the next Nobel Prize is already on the way, perhaps.
But the exoplanets have been written out now. No, but I should always say the Nobel Prize is handed out a bit later, when something, I think, turned out to be useful or fruitful. Maybe less for the gravitational waves, where it was rather immediate that it was handed out. But if you think about the exoplanet field that has now proven very fruitful, and then it goes to the first discovery of an exoplanet. And similarly this year, because the Nobel Prize was not about the work in the past few years, but it was actually about the discovery of that object. And it has now turned out to be extremely interesting, fruitful, and useful for many things. And so the prize looks a bit more backward, I would say.
Yeah. So getting into the specifics of the work that you do. So you look at stars at the center of the galaxy. How close can we get, and how can we be sure of how close we actually are when we're looking at these stars? Is it luminosity measurements or parallax measurements?
It's actually, we can measure the distance to our objects actually very, very precisely. Probably more precisely than the size of your own garden.
Oh, wow.
So we know things to roughly 0.5%. That's pretty good if you compare it, to a human being. That's more or less a centimeter or so. I don't know how to express that in feet, inch, and stones.
Don't worry about that. Nobody uses that. It's fine.
But so the trick is essentially that we can see stars with a certain proper motion, which is an angular velocity on sky, and we measure a radial velocity in kilometers per second. So this is an absolute unit. The other is an angular unit. And we actually have a very good model for the motion of the stars, which is Keplerian ellipses. And that means we can relate these two velocities, and the only factor between those two is the distance. And so we actually have one of the few cases where you can directly measure the distance. So it's actually one of the best known distances in the universe.
Wow.
Because we can measure kilometers per second and relatively assumption-free. Also, the proper motions relate those two, and then you get this very precise distance estimate. It's 26,000 light years, or 8.3 kiloparsec is the distance.
And how far are we from the center of the galaxy when we're looking
I mean,
at these stars?
These stars are extremely close. So they are, in terms of the size of the black hole, they are maybe they come as close as roughly 1,000 times the size of the black hole. So the orbits are elliptical, so that means at closest approach they're much closer than they are on average, but they actually not that far away from the event horizon.
Amazing. And what are the physical and the technical difficulties when attempting to look at individual stars at the center of the galaxy, and how are they overcome? Are we making measurements in visual or infrared or?
So, I mean, the first thing one should say here is that actually what we're doing is extremely simple.
I didn't say that.
It's in a sense, I mean, Newton would have understood himself. If he would have seen those movies which we create, he immediately would have known what's going on. The problem for him would have been the technology, and we are much better in technology, and it's a twofold problem. One is that to look in the center of the Milky Way, we actually have to overcome an extinction screen of dust. Between us and the galactic center. There's a lot of dust. Well, a lot is maybe a bit an exaggeration. If you were to compress all the dust into a single plane, what do you think how thick that would be?
I mean, I'd imagine several million kilometers.
No, it's a sheet of paper. It's.
I knew you were setting me up, and I still fell in the trap. But
So it's a. So that means that you can actually look through this sheet of paper with infrared radiation, and that is the light we are using. Of course, through a wall, there would be no way to look with infrared radiation. You can do so with radio waves. As you know, your mobile phone probably works in your home, and that means the radio waves travel outside a wall. Infrared radiation doesn't do that. So, and the fact that we can look with infrared tells you that the amount of dust is more or less like a plastic bag or a piece of paper or something like that.
Makes sense.
So, and infrared technology is extremely demanding in terms of technology. You have to cool the detector, so you need immediately liquid nitrogen, and that then requires that many of the things you need, like a filter wheel, a shutter, and stuff like that, all this needs to work at those low temperatures of liquid nitrogen, which is minus 200 degrees Celsius. And so that makes it complicated. And the second point is that it's actually close to Earth, but not that close. It's still 26,000 light years, and the scales on sky are rather small. So you need the big telescopes. You need actually the 8 to 10 meters to properly resolve things. And those telescopes severely suffer from the atmosphere under which they stand. So we are standing on the ground, and we need to look through the atmosphere. And that means that really a big boost in the field was the advent of adaptive optics, where one actually can see through the atmosphere without the blurring effects by compensating for that. So the trick of adaptive optics is that one mirror in the beam path is actually shaped such that it corrects what the atmosphere undoes. And the only difficulty is you need to adjust this mirror roughly 1,000 times per second. So it's not a one-time thing, but you adaptively have to control it, and then it's this miracle that the images get sharp, as sharp as they could be, and then the 8 or 10 meter class telescopes really deliver unbelievable images, and that turns out to be good enough to fully resolve out the stellar population in the galactic center. It's extremely rich. It's a very, very dense stellar field. I'm sure if you were to live on a planet around a star there, astronomy would be the major topic in all schools, because the sky would be so beautifully full of bright stars. Yes.
Why is it so? Why are the stars there so large and so densely packed? Is the dense packing just a a factor of the sort of spherical geometry, getting closer to the middle of a sphere?
No, it's actually the stars are denser there, and but the black hole actually doesn't have much of an influence on the galaxy. If you think of the galaxy as a whole, the black hole in the center of the Milky Way weighs 4 million times the mass of the sun, and the Milky Way itself is 100 billion times the mass of the sun. And the radius over which the mass of the black hole is dominant is surprisingly small. It's a few light years only. And beyond that, the stars don't feel the black hole anymore, but they only feel the added gravity of all the other stars. And so the whole galaxy actually makes this potential well, and the stars tend to, of course, cluster in the deeper parts of the potential. And it happens to be that inside there's this little black hole, but it's really just like a fly on your car. I mean, the car doesn't really care about this little fly. The Milky Way doesn't really care about its black hole, so to say.
Amazing. So what do we actually observe when we look at stars near the center of the galaxy? How are they moving, and how does that tell us that there must be this black hole, or at least this compact dark object there?
So, I mean, the experiment started out by theorists saying, oh, there cannot be stars close to a black hole. And the astronomers said, okay, let's look anyhow. And the result of this was that actually there were stars discovered very close to the black hole. And then it's obvious you do it in 1 year, and then you look another year and a third year, and you find out, oh, they are not steady, they move. And you find out that those stars actually move at quite high velocities. And I mean, it was already suspected that there should be high velocities because you could, even before you look at individual stars, you can look at the radial velocity of stars. And even if you don't resolve out, you can look at the radial velocity dispersion. So that means what is the range of radial velocities? You can do this by the width of spectral lines. You can use stars for that, or gas. And it was clear that there was velocities of 300, 400 kilometers per second, which is 10 times the speed of Earth around the sun. So that was pretty high speeds, and that already pointed towards that there is a black hole. But these stars now turned out to be so close that they were actually starting to pinpoint where the black hole actually is. And in 2002, it so happened that then one of the stars for the first time swung around the black hole. And the only explanation for this is a Keplerian ellipse. And with a bit of physics, you can calculate the mass. You don't need, I mean, at least in the better high schools in Germany, you still learn how to calculate that mass. It's not that difficult. So that was a very, very convincing evidence that there actually is a very compact mass.
So I think looking at some of the results, there was one of these stars only took 16 years to go round the entire.
Yeah, well, only you still need a bit of a patience. Yeah. I mean, if I don't know, if your daughter takes 16 years to get a PhD, you get worried. So that's actually quite a long time scale if you think in terms of a PhD student. So you cannot do such a project with a PhD student. Even for a typical research grant, it's the grants are typically 5 years or something like that. So you actually need somebody who can devote more time to it, and that means it's actually a department project, so to say.
Yeah.
But on the other hand, 16 years is still 5 times the star makes it around in the lifetime of a physicist, right? If you live for 80 years, you can see 5 revolutions of the star.
So we can see these Keplerian orbits around the center that's probably a black hole, and then we see that effect dies off as we move further away. So there must be something dark and dense and sort of spherically symmetric that's in the middle of the galaxy. Could it be anything else?
Yeah, there's of course always some loopholes. At least in the 2002 observations, you could come up with strange ideas, fermion balls, boson stars. So this is things where you can put together hypothetical particles, and but many of these solutions actually are not really stable, so they would collapse.
We like to do that in particle physics. If there's a problem, there's a new particle somewhere that we haven't seen before. That's always the way.
So I would say it's actually the most conservative explanation is a black hole. The things you need to construct are more abstruse than actually in a black hole. So that's maybe the best way to put it. And I think it was also in general accepted in 2002, after these observations of the first orbit, that, okay, now we're sure that black holes do exist.
I think mentioned in the Nobel Prize work as well was this idea of near infrared and X-ray flares from a similar position, which could be the accretion flow into a massive black hole.
Yeah.
Is that some more
So
evidence?
there's actually more evidence. So the orbits measure the mass, and this is of course a key ingredient. But we actually, in order to show that there's a black hole, we need to know a bit more. And the second point is that actually there is a radio source in the galactic center, which we call Sag-A star. And that radio source nowadays has a size which is smaller than 0.4 astronomical units. So it fits into the Venus orbit. And it turns out there's actually a few stars in the galactic center which are both radio emitters and infrared stars. And that means that you can locate where's the radio source. You can locate it on top of these orbits. And it turns out the mass is exactly in one of the focal points of the orbits.
Oh, wow.
So you do know that those 4 million solar masses are constrained to a size which is maybe the Venus orbit. and that together then gets very, very hard to have a different explanation.
To argue with those
in addition,
observations.
there come these flares which come in the X-ray and in the infrared bands. Those actually can change rather rapidly. And so by the time scale that they can change within minutes, you can limit the thing to be smaller than a few light minutes. And our observations in 2018, where we have seen actually these flares move, we see them actually move on very tiny levels, has limited the size in which the mass needs to be constrained to something like 10 times the size of the black hole. That's much smaller than the Mercury orbit. So we have nailed it down pretty clearly. Yeah. And you could make another argument. You could even speculate. So if that object would have a surface, what would it do? And it turns out that such a heavy object with the gas around actually will accrete. And even if you take the most conservative accretion flow models, there would still be some material crashing on the surface, heating that surface up. And in equilibrium, that would be an extremely bright surface, which we don't see. And so from the size measurement and the absence of strong thermal infrared emission, you can actually set a limit how much material which falls onto it needs to vanish without creating any impact. And that number is 99.6%. So in a sense, we are 99.6% sure that there is an event horizon.
Yeah, amazing.
So it's pretty tough to argue against the black hole, I would say.
And then I guess this builds on the top of the Nobel Prize from a few years ago with the LIGO results and such. It's very hard to say that this isn't a black hole. It could be something else.
Well, the LIGO results, of course, refer to smaller black holes, which we cannot locate, except in one case, I think, where optical identification was possible. They are a few 10 solar masses, these black holes, and they see the merging of black holes. So that is actually a completely different regime. We're looking here at 4 million solar mass black hole. That's a huge monster compared to those. And actually the history of these big black holes must be very different than of these 10, 20 solar mass black holes.
Makes sense. How common are these supermassive black holes at the center of galaxies? Is the current idea that they're very common? Do they explain things like quasars, for example?
Exactly. So it's actually the other way around, that quasars were discovered first. So, and it turns out that quasars, so the first thing was you see a bright dot in the sky, and at some point it was actually discovered, wow, these quasars actually are at high redshifts. That means they're extremely distant. That means the luminosities they have are very, very extreme, and they are as bright as the whole galaxy, or even brighter. A galaxy consists of hundreds of billions of stars, and there was a source which even could be variable on days, timescale, and people had no idea what it could be. And it was actually then in the 70s that the idea came forward, this must be accreting supermassive black holes. And it turns out, despite the fact that a black hole is a black thing, an accreting black hole is actually the most efficient machine to convert mass into energy. So they can radiate away roughly 30% of the rest mass of the infalling matter.
Wow.
So it's very efficient. If you think of nuclear fusion,
Yeah.
that's at the below percent level, what you can convert of mass to energy. Black holes are much more efficient. And that's how you can explain the quasars. And nowadays, one thinks that essentially all galaxies contain a black hole in their center. When they merge, in the end, also the black holes will merge. And this one-to-one relation, of course, speaks already for a co-evolution of the two, so that actually the black holes and the galaxies form together, and then you're immediately in the question, how do galaxies form out of the cosmic web, and in that process also black holes must form.
Amazing. So you mentioned this just as we sort of come to the end of this. So you mentioned earlier that it might not be much of an effect, but what effects does the presence of the black hole at the center of the galaxy have on our galaxy and even on us? So does there need to be a black hole there for the galaxy to even form around?
No, I don't think so. No, I mean, there's one example. It's the galaxy M33. It's the third galaxy in the local group beyond the Andromeda galaxy and the Milky Way. And in that galaxy, there actually is no black hole. So it seems to be not really every galaxy has it. So apparently galaxies without black holes can exist. However, there is a process which nowadays one is calling feedback. And this is when in these quasar phases, the black holes are they're radiating a lot and they actually emit a lot of gas. And that has, of course, feedback on the galaxy, because the outflows can be so strong that they take away gas and thereby move huge amounts of material around and redistribute gas in the galaxy. So indeed, there's some effect. I think even if the Milky Way black hole would be a quasar, it would not be dangerous on Earth in terms of the radiation which would arrive here. So it would not kill us here on Earth. And it's also clear that we are currently in a very dormant phase in the galactic center. This poor little black hole doesn't get any food. It's starving, and it's very depressing for this black hole. It only eats 100 millionth of what it can eat. Imagine you get such a small dinner, 10 to minus 8 of what you actually could eat. That's not good.
I'd be struggling very quickly.
Exactly. But there's actually hints that the black hole was brighter in the past. So there's hints that there have been much stronger accretion events in the past, which also makes some sense that this is episodic and sporadic, and that most likely this quasar phase is only something which lasts a few million years, and then it shuts off, and then it turns on again. So that makes some sense.
Amazing. So final question, because I don't want to keep you for too long. What can we expect next in this field of work? What is the next exciting thing coming down the track? What do we need still to pin down in this area of work when looking at the galactic center?
I would say the spin of the black hole. How is it rotating? There's many ideas how to do that. You can think of looking for a jet which would point the axis. You can think of frame dragging, so that actually the stellar orbits are dragged around the rotation axis of the black hole. For that, one would need again more precise observations than what we currently can do. There's many ideas how one could approach this, and it's actually the second number of a black hole. An astrophysical black hole has a mass and potentially a spin. It's very likely, since all objects in space seem to rotate, also a black hole should rotate. And that is, I think, what we should hunt next, trying to understand how quickly and in which direction this black hole is rotating. Also, one should say, you've probably seen the black hole image of M87,
yes,
this famous orange ring picture which was there. I think we really can expect at some point a similarly good or even better image of such a star. I do know that data have been taken, excellent data, and the Event Horizon Telescope team is working to get such an image. So
will that be difficult if there's a small amount of accretion onto the...
No, I think the difficulty is rather that such a star is not steady. It's changing quickly on minute time scale, whereas M87 was changing on months time scale. So there's a bit of a difficulty here. The fact that we know the mass so well means that we can very precisely predict what kind of ring they should see. That we can very precisely predict the diameter of that ring. And so that is, of course, and taking those two things together, the observations of orbiting objects and the radio, I think that would be a way forward towards testing general relativity in this wonderful laboratory around the black hole in the center of the Milky Way.
Amazing. I think that's something to look forward to and a really nice place to stop. Final thing, where should people go to find out more about your work, find out more about what's going on with work in the Galactic Center? Where would you like to point people to find out more and get engaged?
Just Google Google Galactic Center Black Hole, and you'll find so many nice illustrations, so many beautiful animations are done. Very nice are the animations which the European Southern Observatory has done. They have a very good graphics department. They made very nice animations of our observations.
They're going to start appearing in the video as we go along. So that's
yeah.
good.
Yeah, those videos are just very stunning to look at, and they are stunning because they are too easy to understand. You somehow get a feeling for what you see there. It's again the fact that the observations conceptually are simple. Yeah. It's only technically challenging, and that's of course the beauty of the experiment.
Yeah. Dr. Gillessen, Stefan, that was absolutely fascinating. I've learned a lot. I'm sure everyone watching has learned a lot. I'd like to congratulate you again on your work and the team winning the Nobel Prize. Thank you so much for taking the time. I know working in science that we never have enough time to do everything. So I very much appreciate you taking the time today. And hopefully when the next exciting thing comes along in this field, we can have another chat. That was fantastic. Thank
you very much for the interest in our work.
Thank you so much. Have a great rest of the day, and hopefully we'll talk again soon.
Yeah. Bye-bye.
Thank you, my friend. Bye.